Hello, everybody. Guess what? We're back. And happy holidays and happy new year. And I hope you guys are enjoying your holidays doing mathematics. We'll start it off with a good one. When do ducks wake up? At the quack of dawn. Quack, quack of dawn. Okay, enough of that. All right, now we are doing a new topic today. We are doing integration. All right. Now, this is going to be one of your most important topics that you cover this year, and it's going to be used in a lot of the other topics that you do. And so this is almost going to be the baseline. It's going to be the bare minimum, so to speak. Now, what is it? I think you guys may have had a slight idea. I'll show you exactly what it is, but for now, I'm going to define it as it's the opposite of differentiation. When you differentiate something, you find the rate of change. Now, all you're doing when you're integrating is, say, for example, if I have the rate of change, I can go back to my original equation. So everything has an opposite, plus has minus, times has divide, exponential has a log. The opposite of differentiation is going to be integration. And I'm going to teach you how to do that. Now, what is it and why is it used? We'll get to the algebra of it in the next lesson, but for today, I just want to explain conceptually what integration does. And it's a method to find the area under a curve. Okay. Now, when I say area under a curve, it doesn't necessarily have to be a curve, but it's just the area under a function. Now, I'll show you in a little bit, I guess, some ways that we already know how to find the area, but then I guess where integration would come in handy. Now, the area is made by bounding a function with the x-axis, and it'll often look like this kind of weird, that S, kind of long S symbol. That's your integration symbol. You're going to integrate between two kind of values, and you're going to have some sort of function, and you're going to have this dx thing. But all that notation, I'll explain as we go. Now, if we're trying to find the area under a curve, let's start with what we know. Okay, so when we say under a curve, I just mean under a function. Let's start with the things that we know. So for example, here, now hopefully this should be a bit of a recap for all your, for all of your graphing. Now here we have an equation y equals 3. And I'm going to use this nice blue color. Okay, so we have this line, that solid line is y equals 3. I could draw it all the way through, and that would be y equals 3. Now, what's happening is I can see here that there's an area that's bound by, I guess, two values, which is going to be, in this case, this value and this value. And I can see that it's a rectangle. So the way that I would say this is, okay, my integration of my line y equals 3 between my two values 0 and 2. And I'm integrating with respect to x because that's all we're really going to do for the time being. It's all going to be that. Now I'm trying to find the area of the shaded region. Now, as you can see, it's a rectangle. So I'm going to write that down. And we can see here a rectangle is just length times breadth. So in this case here, my length is going to be 3, breadth is going to be 2. So in other words, it's just going to be 3 times 2, which in this case is 6 units squared. Now, the reason that we are answering in units squared is because we are talking about an area. Okay, so again, don't stress too much if this part here has confused you. Let's just talk about finding the area underneath. So for this one here, the next one that we kind of already know is we can see this shape here is a triangle. Okay. Now with a triangle, we know that it's half times base times height. That's the area for a triangle. Now here, all I need to do here is let's take a look. It's going to be, my base is 3, my height is 3. Right, I don't know if you can see that. It's labeled somewhat nicely for us. So it's going to be half times 3 times 3. And that's just going to give us 9 on 2 units squared. Now, the way we would write this is we're integrating, and between the two x values. So that means I'm integrating between 0 and 3. So I'm going to write 0 and 3 here. And what's this line here? This line is actually y equals to x. So that's my function, that's my fx. So it's just going to be x. And then again, we're integrating with respect to x, so we write dx. And so that would be how we write our integral. Okay, hopefully this is starting to make a little bit of sense. Don't stress too much. We'll get into the details of that notation in the next lesson. Okay. Now, this next shape here, hopefully you see what area this is. Hopefully you recognize that this is a trapezium. Trapezium. Now, the way you find the area of a trapezium is height on 2 times a plus b. That's just the area formula. So height in this case here, that there is going to be my height. So I can see here that h equals to 2. And then a and b, generally a and b are going to be the parallel sides. So we can see here that this length is 2. We can see here that this length is 4. Hopefully you can see that that's what I'm kind of working with here. So if I was to find the area of the trapezium, the area of the trapezium is height, which is 2 over 2. A plus b is going to be our 2 parallel sides, which is 2 plus 4. And let's just do that. That's going to be 1, 2 on 2 is 1, 2 plus 4 is 6. And so our area here is going to be 6 units squared. Now, again, here's the tough part. Now we're integrating, let's see, we're integrating between the x values of 0 and 2. So 0 goes down here, 2 goes up top here. We're integrating, we're trying to find the area between those 2 points on the x. Now, what's the actual graph itself? I need to find the equation. Now, this line here is going to give the equation of y equals to x plus 2. Right, so if I was to draw this a little bit and extend it further, that's the equation of that line there. Y equals x plus 2, because I have a y-intercept of 2 and a gradient of 1, so it's just x plus 2. So that's what I would write in this little section here, x plus 2, and again, we just write this dx for notation. So that would be that. All right, now we also know how to do circles slash semicircles. Okay. And we know that it's going to be given by pi r squared, or if you want, you can put a theta on 360 out the front of it. Yep. So whatever kind of value of the circle you have. So again, if I was to take a look at this, can we see here that our radius is 2? So in this case here, it's just going to be, using our blue here, equals theta, which is, I guess, 180, or in other words, we have half a circle, so I'm just going to put half out the front, pi times radius squared, which is 2 squared in our case. And this is going to give me 2 pi. And again, you can put that in your calculator, but I'm just happy to leave that as 2 pi. In case you're wondering where that 2 pi came from, let me show you where, so there's no confusions here. It's just going to be half pi times 4, because that's 2 squared. It'll be 4 on 2 pi, just kind of cleaning things up, and that's just going to be 2 pi. Again, units squared, because we're talking about area. So here we're just trying to find the area of the shaded region, and we kind of know how to do all these ones. It's going back to, I guess, simple geometry where you're trying to find the area of different shapes. That's what you'll be doing for this exercise, and that's all you'll need to do. Now, again, I'm going to show this to you just so we can start to get used to seeing what it looks like now. For here, the area I'm trying to find is in between these 2 x values. So that means I'm integrating between -2 and 2. Now, the hard part here is, what is the equation of this graph right now? And I'm a little bit rusty from holidays, but y should be, it should be 4 take away r squared. What is it? Is it? No. 4 take away x squared. I think that's it. that there would be the equation of that. So that's what we'd put here. Square root of 4 take away x squared. Now, again, if you're not unsure of where that came from, this should be good review for all your graphing, which you'll have to look into. Check it on Desmos if you want. And we put in the dx because that's the notation that we use. And again, that there is what you'll be doing for today's lesson. You'll just be kind of going through, okay, that first shape for number 1, that's a rectangle. It's just going to be height, length times breadth. Oh, that's a triangle. We're going to do half times base times height. Oh, we've got a trapezium. That's height on 2 times a plus b. If you've got a circle, then it's just pi r squared. Semicircle is half of pi r squared, so on and so forth. You'll just be finding areas of a curve, the shaded region, and you'll be calculating those. Now, note, we will cover, there's other things in that exercise as an example where you use upper and lower rectangles. I'm not going to worry about that yet, so don't stress, but hopefully that gives you enough of an idea or enough of a start to what you need to do today. Okay, now I don't know if that was confusing or not. Please let me know if that was. Again, bottom line is for the time being, just try to find the area of the shaded region. All this notation will become clear as we go on this topic. So hopefully that makes sense. That should be it. I'll catch you guys later. All right, and bye.